Okay, so, all right, so, I don't remember what number chapter it was, but when we talked about energy, one of the things we talked about was the work kinetic energy theorem, right? And it was this idea that the net work on an object is equal to the change in kinetic energy of an object, okay? So now we've been talking about rotational motion, and specifically right before break we were talking about rotational kinetic energy, okay? So when we talked about work, we learned that you can calculate work by doing FD cosine theta, right? Force times distance times the component of the force that's parallel to the motion. So now we need to learn the angular counterpart. So our work equals FD. What's the angular counterpart for force, you guys? Torque. And our displacement, our change in x, is going to become change in theta. Okay, so the idea is, right now this has kinetic energy, right? And I can do work on it to take away that kinetic energy by providing a torque, right? So the idea is, as my hand produced friction, that friction resulted in a torque that changed its angular velocity, right? So in the same way that work is equal to force times distance, work is also equal to torque times the displacement that the wheel went through during the time it took me to slow it down and stop it. Yes.
How does not on the ground and not to do work?
Say it again.
It's not on the ground. Moving across the board, it's not doing work.
What's not doing work?
It's not. Once it's on top. Like, goes down the circle.
So first of all, we're not worried about what the wheel is doing, but what's happening to the wheel. It's the difference between me pushing you and you pushing me. So the object we're focused on here is the wheel. Okay? So instead of saying, is the wheel doing work, the question you should be asking is work being done to the wheel?
Oh.
Does that distinction make sense? You sure? Everybody okay with that? All right, and so then the question becomes, well, did I do work to the wheel? And to answer that, did I change the energy in some way? Didn't I? When I stopped it, I did, right? Yeah, that's what we're talking about. While I stopped it, I'm changing the energy, and therefore I must have done work on the wheel. Cool? Everybody good? All right, now let's talk about where that energy went. So where does the energy go? Heat, right? Friction between my hand and the wheel produces heat, right? Follow? Alright, so I think what I just said verbally is a lot of what this slide here kind of says. Alright, so we learned a week ago, how to calculate rotational kinetic energy, and we talked about the fact that torque produces angular acceleration to change kinetic, I guess, to change rotational kinetic energy, right? But what's the connection? So this is exactly what I just walked you through, so I guess I probably should have put this up instead of. So we learned that work is force times displacement, right? Okay, and this is all assuming one dimension. Keep things simple, we're just assuming linear here. So we won't even worry about the cosine theta. All right, so the work is equal to the force times the displacement in the direction of the force. And then you can use one of your jumper equations, right? Displacement is change in theta times r, right? Cool. And then you've got three numbers here that you're multiplying, so it's associative, so you can flip stuff around, or commutative, I guess, right? So F change in theta r is the same as FR change in theta. And then force times radius, well, that's the torque that you're producing, right? Okay. So work can also be thought of as torque times the angle that the object rotates through. Okay. So when we learned about work, we learned that work was equal to the integral of your force with respect to the position. And so likewise, this becomes the integral of torque with respect to angular position. Okay, by the exact same logic that we used the first time through. All right, and the work kinetic energy theorem, that your net work is equal to your change in kinetic energy, still holds. Okay, so if your object loses 10 joules of rotational kinetic energy, then there's 10 joules of net work being done, negative, I guess. And when we talked about power, we learned that power was the rate at which work was being done. pointed that the rate at which work is being done, right? And we learned that you could calculate instantaneous power, and I should probably, so this is instantaneous. Instantaneous. All right, so there's our instantaneous power. It's the force times the velocity. All right, and then you can see that you can replace force with torque and linear velocity with angular velocity. All right, so those are both equations for the instantaneous power generated. Okay, so if you wanted to figure out how much power I produced here at a given moment, you would take the torque that friction is producing, okay, and multiply it by the angular velocity that is. Cool? All right, and I'm realizing now what I didn't put up here that I probably should have, there's plenty of room to do it, is this. I don't know when that for color. Average power, you guys remember? How do you find average power? Change in energy over time or work over time. Yeah, work over time. Basically ends up being the change in your energy divided by time. Okay, and that still holds here. It's just a different type of energy. It would be rotational kinetic energy instead of, kinetic. Cool? All right. So, this example that I came up with, there are examples like this in the book, and I've seen similar problems like this on old AP tests. So this is, I think, a really, really good example that hits a lot of important points. And it's going to review some stuff that I think you guys struggled with a little bit when we were doing forces. So I think this is going to hit a lot of important bases here on this example. Okay? So, any questions about kind of what's here? There's not a whole lot that's new, but are we pretty cool with everything? Okay, cool. All right, so what we've got here is what we've before called Atwood's machines, right? Okay, and you guys always joke about pulleys because the pulleys are always massless. Well, in reality, pulleys aren't massless. So we need to find what? So we need to find a way to deal with this because the idea is, when you set this thing up, mass 2 is going to fall, and mass 1 is going to go up, and assuming that the string doesn't slide at all on the pulley itself is going to turn. Make sense? So we need to find a way to deal with all of this and figure out sort of what's going to happen. All right? So we're given a whole bunch of information here. So suppose mass 1 in the drawing has a mass of 0.8 kilograms. So let's make a little note of this. The mass here is 0.8 kilograms. Mass 2 is 1.2 kilograms. The mass of the pulley, if you read through the problem, is 0.6 kilograms, and the radius of the pulley is 0.05 meters. And then it says the pulley can be treated as a uniform solid cylinder. So why am I giving you that information, you guys? So you can find the rotational inertia, right? I know that I, for my pulley, is going to be, well, for a uniform solid cylinder, it's 1/2 mr squared. It's a uniform solid cylinder. Cool? All right, so from there, we got to do some calculations. So. Oh, yeah, it did work. Good. Sorry, just trying to get a little more room on the board. Okay, so everybody good with all that? Did I shrink it too fast, Elizabeth? Are you good? Oh, okay. Everybody good? All right, so A says how fast will it, well, so it says if the system is released from rest. How fast will it, meaning the system, be moving after mass 2 has fallen 0.75 meters? Right, so the idea is mass 2 is going to come down, mass 1 is going to go up, and as that happens, the pulley is going to turn, right? Cool? And I'm wishing now that I'd written this a little bit more clearly to say that assuming the string doesn't slip on the pulley, which is how these problems are usually worded, so I neglected to say that. I should have put that in. All right, so it says how fast will the system be moving after mass 2 has fallen 0.75 meters? So, question?
Yeah, why do you need the inertia?
Because some of our, I don't want to say this without giving away how, that pulley is going to turn, right? How much and how quickly that pulley turns is going to be dependent on its rotational inertia. In the same way that how quickly these masses fall is dependent on their masses. Okay? So that inertia is going to determine sort of how hard it is to turn the wheel, and it's going to affect how quickly it moves. Does that make some sense?
Yeah.
I didn't want to say too much there because I don't want to completely give away how to solve the problem. But does that kind of make sense, you guys? Like if this thing was made of lead and was super heavy, then most of your energy is going to go into just making that thing turn, right? Whereas if it's really flimsy plastic, it's going to spin really easily, and you're not going to lose as much energy there, right? Okay, so that's why. All right, so we need to find sort of a course for how to solve this thing. And there are a bunch of different ways of solving this. But there's one way that I think is probably the most straightforward, and actually, there might only be one way to do it now that I think about it. So, thoughts about where to start? As I was starting to think, oh, you could do this, but I guess you couldn't. So, thoughts about where to start? Sure, what do you got, Nikki? Find change in theta for, oh, I see, to figure out what angle the pulley's going to turn through? Okay. Where would that lead us? I'm not saying it's wrong. I know it's something we need to find sooner or later. I'm just... You're in the ballpark for sure. Here's, I guess, my only concern is this. Is the velocity of the system, and therefore the rotational velocity of the pulley, is that going to be constant? No, it's going to change, right? So you're right. Like if we found that change in theta, don't write this down. We could maybe try to link that to, I don't know, average angular velocity times time. But the problem is this angular velocity is changing, which complicates things a little bit. I don't know that it's a bad direction to go in. I just don't see where it leads you, I guess. I don't know, Nathan, what do you got?
Since we know all the masses, should we just find the acceleration of the system?
Tell me how I would find the acceleration of the system.
We could use like the masses of the two blocks to find like the gravity pulling them out.
Okay, so let's think about that for a minute. So maybe here's another thing we should do. And again, let's not write any of this down. I'm just trying to kind of help us figure out how are we going to solve this mess. So let's focus on mass 1 for a minute. So here's mass 1. So what you're telling me is that gravity's pulling this down, right? Tension is pulling it up. So I know this, but I don't know that tension, do I?
You can only pass two. You have to take the
Okay, so here's the weird piece, you guys, is so up until now we've always had that the tension at both ends of the string is the same. It turns out that that's not the case here. Does anybody see why? Because of the pulley. Yeah, some of this is said a little bit sloppily, but basically some of the force from the tension is used in turning the pulley. Okay? So the tension is greater in one direction than it is in the other direction, which makes things more complicated. So I guess I'm not sure I see where we're going to go from here. We can certainly find this force of gravity, and we can do the same thing over here, but we don't know these two tensions. We know our displacement. Is there something I'm missing, Nathan?
There's just some slow that.
Yeah, no, and that's okay. That's right. All right, Alex, you had a hand up before any of you. I gotcha. Yeah. Say that one. Oh wait, say it again. I was thinking about this for a second, so I lost track of what you said. Say it again. So the reason that I put this in the work and energy section was because we need to think about energy. All right? So as the system moves, what's going to happen is mass 2 is going to lose potential energy, and mass 1 is going to gain potential energy, right? But which gain or loss is going to be bigger? Yeah, mass 2's loss is going to be bigger because it has more mass, right? So where does that energy go? Turns into kinetic energy. Specifically, the kinetic energy of mass 1, mass 2, and the rotational kinetic energy of the pulley. Okay. So, instead of saying it, let me show you. All right, so let's do this. So A. So let's focus on mass 1 for a minute. Let's find the change in gravitational potential energy for mass 1. Okay? So let's see. Gravitational potential energy is mgh, right? So our mass is 0.8 kilograms. G is 9.8 meters a second squared. And mass 1 is going to go up 0.75 meters, right? So we're going to gain, we're calculations. Oh, that's honors AP, here we go. So mass 1 is going to gain 5.88 joules of gravitational potential energy. Follow? All right, now let's do the same thing for mass 2. So if you do this, you get 8.82 joules. But there's an important difference. Other than the fact that numerically they're different, it's negative, right? Because mass 2 is going to go down 0.75 meters. Therefore, we're going to lose that much gravitational potential energy, right? So for our system as a whole, our change in gravitational potential energy is going to be these two things added up, right? This one gains this much, this one loses that much. So 5.88 joules plus negative 8.82 joules equals negative 2.94 joules. All right, so let me pause there for a minute. I see some people processing. Marcus?
Oh, I was just wondering. Oh, okay, got it.
Sorry, my KGs are always...
Okay, so that's mass 1, mass 2, and the pulley?
Well, is the pulley moving up or down at all?
So that's just...
What kind of potential? Is everybody okay up to there? All right. So I guess the next thing we should ask ourselves is this. Are there any non-conservative forces that would cause our total energy to change?
Yes.
Like what? Gravity's conservative, so we don't need to worry about gravity. That's okay. That's why we're doing this. That's okay. Gravity's conservative. Gravity will never change your total energy. Okay? So we would need a non-conservative force, and it would have to be external. Okay? So I think that's it, right? It would depend on the situation. I guess, no, that would always be external. Friction would always be external. Oh, no, I guess not, because here it's friction between the string and the pulley, so that's internal. So that's internal. All right. So there are no non-conservative forces doing work, so that means that our total energy is going to be constant, right? Follow? So we lost some gravitational potential energy. So you must have gained that in kinetic energy.
How do you number?
What do you mean? Like which object gained which? Well, that's what we got to figure out. All right. So let me buy us a little room here on the board. I'm gonna oops. Okay. So that means that our change in kinetic energy has got to be positive 2.94 joules, right? So now we need to come up with an expression for the kinetic energy of our system. So, what's our starting kinetic energy? I guess we should probably start there. 0, right? So this really is going to be equal to our final kinetic energy, right?
Yeah.
Because we're starting at 0. Okay, so let's see. The kinetic energy of the system is equal to the kinetic energy of mass 1 plus the kinetic energy of mass 2 plus the kinetic energy of the pulley. Okay, well, let's see what that is. So we've got 2.94 joules equals 1/2. Let's see, mass 1 is 0.8 kilograms times its velocity squared, plus the kinetic energy 2 is 1/2 of its mass, which is 1.2 kilograms times its velocity squared, but it's the same velocity, right? Because the whole system is moving together. Yes. But that's force. Here we're working on velocity. The whole system is moving together at the same velocity, right? Where am I losing you? I mean, that's not even...
I'm confused why they can't, like, why there's different forces with different objects.
Because they have different masses. So it's going to take a different amount of force to get the object moving at the same speed. Right? Like, isn't it going to be harder to get this thing up to some speed than it is to get this thing up to that same speed? Because it has a different mass, right?
It's not this is confusing me, it's the previous statement that's confusing.
Which one?
The one that, like, the pulley takes away.
I gotcha. Okay, we're going to do some calculations that I think will sort of help that fit together. Okay, so bear with, because question C and D, question C says what's the tension in the rope on each end, so we'll calculate it and you'll see what happens. And we'll also talk about the force that makes the pulley spin. Cool? All right. And it looks like we may not finish this example today. And if that's the case, then fine, we can finish it up tomorrow. Yeah, Marcus.
So, the mass at the same velocity as the pulley's rotational velocity.
You're warm, except you can't set velocity and rotational velocity equal to each other because they're different units. So you got to use a jumper. Okay, so now when we talk about the kinetic energy of the pulley, that's, and here's where Marcus's question is totally relevant now. Kinetic energy of the pulley is 1/2 I. Did we find our I? We didn't, but I at least wrote an expression for it. It's 1/2 mr squared times omega squared, right? Follow or no? All right. I guess I could have put in my mass and my radius. I don't know why I didn't do that. What am I going to do with this omega, though? Think about... Shoot. I'm going to draw the pulley. So here's the pulley, and the rope is going to pull the pulley around which way? This way, right? So if you imagine one point on the rope moving with some velocity at a radius of whatever the radius is, then shouldn't that angular velocity just be v over r? Follow or no? No? The pulley is turning, right? The rope is on the very outside edge of the pulley. So the idea is if my system, I'm going to pick an arbitrary number. So suppose the system is moving at whatever, 4 meters a second, right? Well, that means that a point on the outside edge of the wheel is turning at 4 meters a second. And I know the radius, so I can use one of my jumper equations to rewrite that angular velocity in terms of the linear velocity. Follow, you guys? This, what I'm about to do here, is a really, really common trick that you need to familiarize yourself with. Whenever you're dealing with these angular quantities, you got to be able to deal with these jumpers. Okay? So this becomes, I'm just going to rewrite this term, becomes 1/2 of 1/2 mr squared times v over r squared. And what happens, you guys? The r squareds cancel, right? Follow? We ran into that exact same thing with when the wheel was rolling, that we, before break. Everybody good or no?
We'll always be given the inertia equation.
Yes. Yes. Oh. All right. So let's plug this in. What do we get? You get 2.94 joules equals, let's see, this is going to be 0.4 kilograms times v squared, plus this is going to be 0.6 kilograms times v squared, plus you've got 1/2 times 1/2. This mass here, you guys, is 0.6 kilograms, right? Because it's the wheel. So you get 1/4 of 0.6, which is 0.15 v squared. Make sense or no? I kind of skipped a little bit there, writing up numbers. Good. So look, everything's now in terms of v squared. That's not too bad. It's a big long equation, but so you get 2.94 joules equals 0.4 plus 0.6 plus 0.15 is 1.15 v squared, and solve it. And your v ends up being, it's really close to 1.6 meters a second. Good? Questions on what we did there? Okay. All right, so our yeah, that was part A. The rest goes a little quicker, though. All right, so part B, what's the angular acceleration of the pulley? Ideas about how to find that? So this one, there are a bunch of ways to do this. Oh no, I'm not there yet. Okay. Talked about how to find the angular acceleration?
I was just thinking, it's just saying, take the derivative of the velocity, so it's just 0.
Very good.
I know.
Yeah. Yeah, that's the velocity at that instant, but not in terms of time, yeah. I know. Okay, so, but your inclination is right. So when you find the derivative of velocity, it gives you acceleration, right? Well, our forces are all constant. That means our acceleration should be constant, right? So let's find the acceleration using one of our constant acceleration equations. Here's what I know. I know that my starting velocity is 0. I know that my final velocity is 1.6 meters a second. I know my displacement is 0.75 meters. I ought to be able to find my acceleration using that guy. Right? That's one of the constant acceleration equations we learned 7 years ago. Perfect.
I thought that was an angular velocity.
Say that again?
But that's not angular velocity. That's we're using jumper.
Yep, what he said. Yep. So the idea is, and it's a good question, the idea is that we're looking for angular accelerations, but most of the values I've got here are linear. So find the linear acceleration, and then just like Jack said, use the jumper to then find the angular acceleration. Good or no? Okay, so if you plug these numbers in, your acceleration ends up being, I think it's 1.7 meters per second squared. Is that right? Yes. So that means that my angular acceleration should be a over r. So 1.7 meters a second squared over 0.05 meters, and it gives you about 34 radians per second squared. All right, are we good? Everybody set? Okey-dokey. So next order of business, question C wants the tension of the rope on each end. So C and D are going to be really closely related and will hopefully help those of you that were worried about, like Patrick, you were saying before, I don't understand why the tensions are different. Hopefully question C and D will help, or maybe it's Alex, sorry. All right, so here we go. So question C. Find the tension in the rope on each end. So what do I want to do here, you guys? Yeah, look at mass 1 and look at mass 2, right? So here, let's do mass 1. So mass 1, here's what I know. 0.8 kilograms. Gravity's going to pull it down with a force of 7.84 newtons, right? This 0.8 times 9.8. I know my acceleration is going to be upwards at 1.7 meters a second squared. I can't say this enough, you guys. If you know the acceleration, you should find the net force, right? Anytime you're doing a problem with forces, if you know the acceleration, right away, write an expression for your net force. And for us, it's just, when we know the mass, we know the acceleration, right? And so that gives you 1.36 newtons. Good? You good? Okay. Everybody good? All right, so now I can find the force from the tension, right? It's got to be big enough so that this is 1.36 more than that, right? Because it's got to be upward, right? I guess I could have made this negative to clarify. I don't know if that helps any. So this ends up being, I'll just write 7.84 plus 1.36, and it gives you 9.20. So that is the force of tension on side 1. Cool? Any problems? All right, do I need to write out the calculations for mass 2? It's the exact same thing, just different numbers. And then, so similarly, the force of tension on side 2 turns out to be, and if you do the math, you get a bigger number, 9.72 newtons. Cool? So sloppily, this is a little sloppy, and I'll give you a better explanation for a minute. But the idea is tension, the mass over here is providing a tension of 9.72 newtons, pulling this way. And some of that tension sort of gets used up turning the wheel, and what isn't used turning the wheel goes to lifting mass 1. Similar to if you push 2 boxes with X amount of force, some of that force goes to moving the first box and some of it goes to moving the second box, right?
So the difference between the two is the work.
The difference between the two is the net force on the wheel that produces the torque. Cool? All right, so is everybody good with C? Okay, let me see if I can get through D. What do we have, 3 minutes? Yes, that's enough time. Let me get through D, because I think it'll tie these things together, and then we'll have to do E and F tomorrow, but those will be quick.
Had a wonderful break, and that you're having a great first day back. Just wanted to make you aware of a few changes in the main office. In particular, Mr. Flint has taken an extended period of time off. And so in the
All right, so here's what I want you guys to do. We only got a couple minutes, but so question D says use 2 methods to find the net torque on the pulley. So here are the 2 methods. So option 1, net torque equals I alpha. Look, we found our alpha in part B, and we know the equation for I. Try it, see if it works. Okay? Option 2. Oops. Option 2, here's the deal. Here's your pulley. There are 2 forces on it. You've got 9.2 newtons pulling it this way, and 9.78 newtons. Is it 9.78? Oh, 9.72 newtons pulling it that way. Both of these are 0.05 meters. So find your net torque using force times distance. Find the torque from this, and add them up. Keep in mind, one of them, depending on how you do your sign conventions, one of them has to be negative, right? I guess for us, this one's going to be negative, right? Because that's clockwise. Cool? So, calculate the net torque both ways, and hopefully you get 0.026. And I guess actually it's negative, the way I've got my drawing set up. Cool? All right, we'll stop there. So tomorrow I'll do these last couple examples and I'll answer questions on the middle homework chunk. All right. The last homework chunk, do you guys want to make it due Wednesday or Thursday? Whichever day it's not due, I'll plan some other kind of reviewy, concept-y stuff. Who wants Wednesday? Who wants Thursday? Okay. That's what I figured. All right. So Wednesday we'll do some concept-y stuff. Okay. Yes. I know. I realized that. It's totally my bad. Sorry. I actually had it blank all weekend, and just today I changed it to an I. And oh.